All right, so let's come back and continue. So we have introduced the concept of inverted index. All right, so it's a key value uh, pair. Sorry, for each key it is a term, and for the value is a list of document ID corresponds to the documents that contains the key. Right. Now let's yeah, all right. So search using inverted index. Given a query Q, so remember query Q is like A and B or C, yeah, such kind of format, right? So the search has the following step. So step one, you find each term in Q in the inverted index. For example, in the example, in the example here we have A, B, and C, right? So find the corresponding list of A, B, and C. By the way, all right. So here we also call this posting list. Right. So you got the posting list of A, B, and C. Then you merge the result. You merge the result or merge the posting lists to find document that contains all or some of the words or terms in Q. So basically you find the documents that satisfy the query's condition. Right. So I will give a concrete example here, but again, this is not the focus of this course. So we will briefly introduce or give an example about a query of Brutus and Caesar. Right. We won't introduce more operations like or not in this course. Again, if you are interested, you can enroll the course of 6714 next trimester. All right, so given the query Brutus and Caesar, as the first step, you locate Brutus in the dictionary, retrieve its postings. Right, the postings of Brutus and the postings of Caesar. Then you merge the two postings. Now assume that this one is the posting list of Brutus and this one is the posting list of Caesar. You walk through, because we're going to do AND, means we want to find the document IDs that appears in both posting list corresponds to Brutus and to Caesar. Right. So it appears in both of these two posting lists. So we walk through the two postings simultaneously in time linear in the total number of the posting entries, and we can find the elements that appears in both of them. So I think the algorithm itself do not need further explanation, as you should know it from other courses like data structures. So we've finally got the answer here would be 2 and 8. So if the list lengths are x and y, the merge takes big O of x plus 1 operations. All right. In order to do that, a very important point is that the postings are sorted by document ID. So this is very important, and we will see in later from next slides in our design of the MapReduce program, this sorted by document ID property is important, and we need to preserve that. Now the next thing and the essential thing in this course is how do we MapReduce it, right? So let's look at let's take a high-level profiling of the index and retrieval problems. Right. So for indexing problem, scalability is critical because we are supposed to be able to handle a large amount of documents or a large size of document collection. And the procedure of indexing should be relatively fast, but no need to be real time. All right, and so fundamentally speaking, it is a batch operation. So each time you take a batch of documents in, right, and incremental updates may or may not be important. So generally speaking, let's say in real applications, the update is not, let's say the update is not in real time. So it's more like updates every week or every day, depends on the application. Right? So basically, it looks perfect for MapReducing. So for MapReduce, right? Because MapReduce can handle a large amount of data, right? It is relatively fast, but not real time. I mean, even we use Spark, it's not that real time. I mean, because we still it still involves traffics between machines in the cluster, right? It's a batch operation, just like we do in MapReduce. We have a block, we have partitions, right? And incremental updates may or may not be important. In MapReduce, we don't really welcome incremental updates, but well, it can be done, but not too frequently. So basically, the index problem is perfect for MapReduce. On the other hand, the retrieval problem, it must have a sub-second response time as your experience on Google's search engine, right? And for the web, we only need relatively few results, right? So we don't, as you can see in Google, you probably just view the first the first page or the first 3 to 5 pages. That's kind of the maximum. You don't expect to see all the results, right? You just want to see a few results. That's fine. So this is not so good for MapReduce, right? Especially the response time. It is a real big challenge for MapReduce. Therefore, we only focus on the index construction, and also the index reconstruction or the index update depends on the application. So now let's just look at index construction, all right, and how to use MapReduce to finish this job. So if we view the index construction from the MapReduce perspective, we see the first thing is to nail down the input and output. So for index construction, the input would be a collection of documents. They formed like as a key value pair if we like. So the key is document ID and the value is the document content. You definitely have a lot of such key value pairs. Now the output of MapReduce would be the inverted index. So again, the key would be the term, if you still remember, and the value is the posting list, which is a list of document IDs. Right. So for example, the term is long. The document IDs, remember these are sorted. I've mentioned here. So the document IDs are 1, 23, so on and so forth. They're sorted. So the document ID is an internal document ID. So it's just a unique integer. So it's not an external document ID such as URL or whatever. So the whole purpose of having this is for the sorting and also for MapReduce. Right. So now, as we already have the input and output, the next question is how to do it within MapReduce. So the MapReduce for such kind of inverted index is kind of simple. Right. So each map is more or less a document parser. Right. The input is a stream of documents with a document ID like 1 and 2 and document contents. Right. So for the output, we just output a stream of a term and document ID tuples. Right. So in order to do that, we just split or pass the document, and for each term we use it as the key, and we use the document ID, for example 1 and 2 and so on, as the value. This is the output of the mapper. We probably do some combines within the mapping, and then for the reducer, it converts streams of keys into streams of inverted lists. So yeah, here the input of the reducer, well, this is not very precise, but it is more like a long one, long 127. This probably could be long. They should be sorted. So here should be this could be from one partition, and you've got 49 and 23 here. All right, so it is just a set of term document ID lists, such kind of key value pairs. Right. These are the input, and the reducer will sort the values, right, the values of the document ID for a key, and builds an inverted list. And remember, the longest inverted list must fit in the memory. Yeah, this is both for MapReduce in Hadoop and in Spark. And for the so here comes the output. So the key value pairs would be key, again, is the term, and the value is the posting list, corresponds to the term. So then we kind of finish the index structure construction for this kind of to support the binary term retrieval, right? Binary term retrieval. All right. So now let's make the problem a little bit harder, right? Now we consider a ranked text retrieval. Now, previously we don't have rank, and now we have rank because with this kind of rank text retrieval, we can present the results on one screen at a time, and with the best result first, right? And at any time or any point, the users can decide to stop looking, just like your own experience of using a Google search engine. All right. So about the rank, how do we order the documents? Right. So we order the documents by how likely they are to be relevant to the query. So in order to do that, we need to estimate the relevance between query and document I, the I's document. Right. Then we sort the documents by relevance, and we display the sorted results. So how do we estimate the relevance? Right. So we assume that the document is relevant if it has a lot of query terms, or say it shares a lot of terms with query. Right. So this is how we decide whether a document is relevant. Then we replace we use the relevance between query and document I as the similarity between query and document I. Right. Well, if we present queries and documents as vectors, then we can use the similarity of the vector representations of queries and documents as the similarity between or the relevance between queries and documents. So this idea is commonly used, is known as a vector space model, and the cosine similarity is used to measure the similarity between two vectors, hence the similarity between two documents, or the query and the document. And also it is widely used in information retrieval and language models. Right. So the problem here is, assume document is relevant if it shares terms with, or just shares a lot of terms with queries, kind of vague. So we come with a more detailed or better measurement of this relevance. So basically the idea is that, also the intuition is, when we look at a term, we say if the term appears often in a document, then that term should get high weights, because in that case the term is kind of represent the document, or maybe reveal the topic of the document. All right. But on the other hand, the term that appears in many documents should get low weights. This is also easy. For example, terms like the or that, right, or in, this kind of terms or words appears in almost every document. Are they important? No, right? Simply because they appear in every document almost, they don't have the ability to represent any of the documents. So our goal is to find those terms that appears often or multiple times in one document, but not appears across all the documents. Right. So here comes the term weights consists of two components that is corresponds to the intuitions. So the local weight corresponds to the first intuition. So this measures how important is the term in this document, in the specific document. And the global weight is how important is the term in the collection. So we want local weights to be high and global weights to be low. So how do we capture this mathematically? So for local weights, we use a term frequency. Right. Also noted as a TF. So for global term weights, we use IDF, which is the inverse document frequency. This inverse because we want the document frequency to be low. In that case, the inverse document frequency would be high. Right. Now let's look at the formula here. So the weight of I and J, where I is the term and J is the document. So there are two components of the term weight. The first one is the TF, which stands for term frequency, and the second one is the log of a big N over a small ni. So term frequency is the time of occurrence of term I in document J. So it is how many times you see term I in document J. Right? This is TF. And N is the number of documents in the entire collection, and Ni is the number of documents with term I. Right. So in this case, the more the more documents that term I appears in, this log N over Ni would be less. Right. So we use this TF IDF term weight to measure the importance of a term. Then, as you may then a document is a collection of terms, and a query here is again a collection of terms. So what we do is so the document would be we represent the document with a vector where each element is a TF IDF weight of, this is for W1 and this is for W2 and so on and so forth. And for the query, we do the same thing. So just remember here that the length of the vector is n, which is we don't use n here. Is v, which is the vocabulary of the whole collection, so we don't lose any or miss any terms. Right. So if the document does not contain a particular term, it will assign a 0 to that element. And so we the same for the query, and we use the inner product of document and query. Let's see, document inner product of document and query as the similarity. Okay. So the retrieval in a nutshell, right? We look up the posting lists corresponding to query terms. We traverse postings for each query term, and we store partial query document scores in accumulators, and then we select top K result to return. So here, the first two steps is to filter those documents that does not even share a term with the query, right? Because in that case, the inner product would be 0, right? Because let's say, so if the doc is 1, let's say, yeah, the doc is 101 and the query is 010, means they do not share any terms, then the inner product would be 0. So it is meaningless to compute the inner product between query and that document. All right. So we use this as a filter step. Then we store then for the next 2 steps, we compute the similarity, and we do the sorting. We get the top key result to return. All right. So again, I mean, retrieval is not the key point of this course. Here is just to give you an idea. So more importantly, what we really care about is how do we do MapReduce in order to construct the index. Now again, the input and output. Right? The input is documents. So it's document ID and document content, just like before, right? So for the output, before we just the output is a key value pairs where the key is the term, and the value is a list of documents. But now it is different. Except the document IDs, we also need the weights, the TF-IDF for each document corresponds to that term, right? So here the output would be the key is the term, but the value is a list of document ID weight pairs, right? So for example, the term is long, and here the document ID is a 123, 49, 127, and the weight, the TF-IDF weight is 0.5, 0.2, and so on and so forth. All right. And again, the document ID are sorted because in the query phase, we need to do the filtering. We need to find those documents that shares at least one term with the query, so we need them to be sorted. All right, so how this problem differs from the previous one. All right. So basically, the whole difference is about the TF-IDF thing. So we need to compute TF and compute IDF within this whole MapReduce procedure. So for TF computing, it's kind of easy. I mean, because one document, because the term frequency is only corresponds to one document, and one document will only be processed by one executor. Right? So it is easy in a mapper. Instead of simply construct the posting list, we also add the number of times that this term occurs in this document. Right? So TF is kind of easy to compute, but for IDF, the thing is for the IDF part is log n of big N over small ni. This big N is already known, but this ni stands for how many documents does this term ti appears in. This thing will not be known until we got all the documents that contains the term t. Or in other words, it is very possible that we can only know this ni until the reduced part. So again, let's look at index of the example of the inverted index with a TF-IDF weight at first, and then let's discuss how to use MapReduce to construct the inverted index. All right, so again, these are the documents. and the left part is how we compute TF and DF, which is document frequency within this matrix. So for example, fish, right? It appears 2 times in document 1. That's why here is a 2. It appears another 2 times in document 2. So here's 2 again. It appears in 2 documents. Therefore, this is a 2, right? And also for the other terms as well. Then you build this inverted index with, this is the key and this is the value. So for the value, you put df first and then a posting list where here the pink one is the document ID and the blue one is the term frequency. And you would you would have a document ID. So it should be like, so the value should be like df document ID and tf, another document ID and tf, and so on and so forth. So this is what an inverted index with a TF IDF weight looks like. So when you have this kind of inverted index, you can actually compute the TF IDF, because it's just TF times log of n over ni. You already have ni, which is df. You have n here as a constant number. So with this list, you can compute the TF IDF weight for each and every term. All right. Now, how do we use MapReduce to achieve this goal? So a simple approach, or say the baseline method, would be kind of simple, right? So for each map task, again, it's a document parser. The input is document ID and document contents. The output would be a stream of a term and a document ID TF pairs as a list. So a tuple of these 2 elements. These key value pairs as a tuple. For example, for long, you have it's in document 1 with term frequency 1, right? A girl with in document 1 with term frequency 1 as well, and so on and so forth. So for the reducer, it needs to convert the streams of keys into streams of inverted lists. So again, the input would be key value pairs. Well, this is the key, and the value is a list, unsorted, right? Unsorted, because they come from different partitions. Then the reducer would sort all the values from a key and builds an inverted index, right? So the computation of TF and IDF would be in the reducer, right? And then the output would be a term and a list of document ID, a pair of document ID and TF IDF weight as the final output. I realized that here there is an inconsistency. So in this example, the value should be this is not right. The value should be a document ID and TF IDF, and another document ID TF IDF, and so on and so forth. Right. So here the example is slightly incorrect, but it does have some. It does show us some idea about the computation of TF and IDF, which actually will be used when we later try to improve this simple approach. So if we take a MapReduce view, these are the input, the documents, and for map, it got for each term, it has a pair of document ID and the term frequency. So after the shuffle and sort, the values are aggregate the values by keys. For the reduce part, we actually get this as input, and then finally the reducer will output the expect result. Now, in order to improve this simple approach, we need to first identify where the inefficiency is. Right. So here we use terms as keys and postings as values. Then the document IDs are sorted in reducers, as you can see here. The input of reducers is unsorted, right? And the IDF can be computed only after all relevant documents received. So you can imagine that the reducer is waiting for different workers to send him the posting lists or partial of the posting lists, and only when it got all the partitions, then it can compute the IDF, as the IDF is actually the number of document ID term frequency pairs to that term. Right. And also the reducers must buffer all the postings associated with the key in order to do the sorting. Right. So if the postings are too large or too big, then it is possible that we will run out of memory. So although, yeah, when we run out of memory, we can kind of put some of them to the hard drive and do the sorting based on memory and hard drive, but apparently this will bring much time cost, right? Much more time cost. All right, so in order to make the improvements, the first improvement is targeting at the sorting part. So we know that sorting the document ID in reducer is costly. On the other hand, we know that the key is always sorted by the framework, by MapReduce in Hadoop or by Spark. Right? So the sorting of key, when do the shuffling and sorting part, this is handled by the framework. So in general, the framework is handled it better than our implementation. All right. So that's the idea. So what we want to do is that we want to do this value to key conversion, also called a secondary sort. So the idea is that the mapper output a stream of, if you still remember before, it is a term and a list where each of them is a document ID and TF. And now the mapper outputs a stream of the key is term and document ID, and the value is TF. All right. So as this is before, the key is term. The values are a list. So it is actually a list with document ID and TF pairs. But now it outputs, let's say now the keys turns from 1 to be 6, right? So it's actually 6 tuples. Before it's 1 tuple. Now it's 6 tuple where the keys are terms and the document IDs, and the values is the term frequencies. Right. So by doing this, as you can imagine, the framework would sort the keys based on not only the term but also the document ID, such that the reducer would be able to get a sorted list. So the sort is not done by the reducer. So the idea of secondary sort is that we don't buffer values in memory and then do the sort in the reducer. It's a bad idea. I have explained this before. So we do this value to key conversion. So we kind of convert the value to be key or part of key, right? So in our case, we form the composite intermediate key, which is the term and the document ID. And we use the term frequency as the value. Right. So then the execution framework will do the sorting for us. Right. And we also need to guarantee that all pairs associated with the same term are shuffled to the same reducer. In order to do that, we need to use partitioner. All right. So we have discussed about partition and partitioner before. Right. So we use a partitioner to make sure this happens. Then the reducer does not need to do the sorting by itself. All right. So this is the first improvement, and for the second improvement, now we if you remember, in order to compute DF, the data frequency, we need to have all the postings, or we need to buffer all the postings associated with the key, and then compute the document frequency. Now, as we already have this as key and this as value, we still need to wait to see all the fish here, and to count the document frequency. So as I have mentioned in that incorrect illustration of TF-IDF inverted index, we do want to store the the document frequency at the front of the posting list, right? But we don't know the document frequency until we have seen all the postings. So in order to get the document frequency, we can do the following things. So in the mapper, we emit a special key value pairs to keep track of document frequency. And in the reducer, we make sure these special key value pairs come first, so we can process them and to determine the document frequency. So here we use this star as a special key, and the value is the document frequency. So the mapper does not only emit normal key value pairs, it also emits a special emits special key value pairs to keep track of document frequency. So with that, for the reducer, it firstly computes the DF by summing contributions from all special key value pairs. And then with the DF, it will then merge the posting lists, the rest part of the posting list. So it is important that we properly define a sort order to make sure that special key value pairs come first. In our case, I mean, in the real application, in the real application, we can define this sort order as we use this star as should appear before any other numbers, or we can use -1, for example, because the document ID would never be -1, right? So basically, the mapper would additional emits a special key of the form that is WI is the term, and star is the special key. Sorry, here should be TI. And the value associated with the special key is 1, because the mapper takes one document each time, right? So the value is 1 because it means this term appears in that document. Okay. This partial marginal counts will be aggregated before being sent to the reducers. When we have multiple documents, we can aggregate the counts based the counts of the DF and also the we can aggregate the counts of the DF across different documents for the same term. All right. So for the reducer, we must make sure the special key value pairs are processed before any other key value pairs. So we need to define a sort order, and we also need to guarantee that all pairs associated with the same word are sent to the same reducer. That part we can use a partitioner to finish, to achieve. So a few more words about this order inversion thing. The memory requirements is minimal because we only need the marginal, which is an integer. We only need the marginal to be stored, right? And there's no buffering of individual co-occurring word, and there's no scalability bottleneck because the reducer does not need to wait all the postings. I mean, to put all the postings in the buffer or in the memory and to compute the document frequency. All right. So the key point for order inversion, you emit a special key value pair. You control the sort order to make it processed first, and you define a customer partitioner for routing the intermediate key value pairs to the reducer. So this is order inversion is a common design pattern in MapReduce. It is used when you are computing relative frequencies, requires marginal counts, and this marginal cannot be computed until you see all the counts. Right? So you don't want to do the buffering. Therefore, the trick here is to getting the marginal counts to arrive at the reducer before the joint counts. Here in our case, the marginal counts is the df, and the joint counts is the tf. So that's pretty much for today's lecture. And also here we finish the introduction of not introduction anymore. We finish the MapReduce part in this course. We have explained the MapReduce procedure or the process in both Hadoop and Spark. Right? We have introduced a couple of operations of MapReduce or of RDD in Spark. We also show 3 different applications using MapReduce. So I do hope that all this gives you a whole picture of what is MapReduce and how to write, how to use MapReduce, how to design a MapReduce program, and also those methods in PySpark as well. How do you manipulate RDDs? Yeah, and hopefully you can make use of all this knowledge in your first project. So I will talk a little bit more about the project since there are students asking. The project is expected to be released in next week. So the teaching team is finalize the project doing the last round of testing. We do hope that everything is correct before we release the project. So the project is to test your ability of design a MapReduce program to solve a real problem. The problem is the problem or say the algorithm that you're going to implement using MapReduce is going to be introduced in next week. So it's a high dimensional similarity search or nearest neighbor search algorithm. And you are required to use only MapReduce and written in PySpark to implement the algorithm. And you are encouraged to implement you are encouraged to improve your implementation to achieve a better efficiency. And the marking criteria for the project, there are 2 components. One is the correctness of your implementation. Another is the efficiency of your implementation. So basically, if your implementation is too inefficient, you will lose some of the marks. And we do encourage you to improve your implementation. So if your implementation is very efficient, we will actually do a contest, and we will assign a bonus for those winners of the contest. So it means if your implementation is the most efficient one over the whole class, you will get the bonus, the most bonus points. All right. It should be the top 20 students will get the bonus. So try your best. Right, try your best on the project. So if you have any questions about the project, definitely after the release, post your question in Piazza and discuss it with your classmates and with the teaching team as well. All right. So that's pretty much for today. Thank you for watching, and let's see